Okay, welcome to the 7.1 video, Introduction to the Normal Curve for the Stats unit. Alrighty, statistics is kind of like the opposite of probability, but this year we're going to kind of put them together. Freshman year you did stats, sophomore year you did probability a lot. This year we're going to kind of combine the two into what we call statistics. But we're going to start with something called the normal curve, something that's used a lot in statistics. We're going to jump on down. You can read all of this about data gathering wherever you want. But we'll look at these three graphs. This is what we call the normal curve. Now yours is obviously not green, but this is how most data in the world happens. My kind of premium example is grading scales, right? When you take a test, or a class takes a test, or a bunch of people take a test, this is usually what happens with the scores. You get a lot of people who kind of get the same score of something, and then you get some people who get less than that, and you get some people who get more than that. You get the smarty pantses over here who get really good scores, and you get the people who clearly didn't study, right? So this happens with a lot of stuff. Therefore, it gets the name. It happens so often that we give it the name the normal curve. Things that aren't normal tend to have a skew to them. So this, for example, is not normal because it is leaning. Clearly people here, a lot of people got a really high score, but then at the same time you get a lot of people down here who got low scores. So it's maybe a test that was a little too hard. You had a lot of people scoring under, and so it looked really dramatic to one side. Kind of the same thing here. You don't have to have the bars. You can have it with just a line. This is a normal curve, nice and perfect. Kind of looks like a bell. Sometimes you'll hear it called the bell curve. Over here, this one's clearly not. You see it shifted. So what it comes down to is how much do we consider to actually be symmetrical, right? Because if something is like this, where it's kind of leaning, do we say, is it normal enough? That's where we get the empirical rule. The empirical rule, oops, pardon me, didn't want to delete that, but that's okay. The empirical rule says there has to be a certain amount that actually is in between those two, that bump, that actually, so it's actually a normal curve, sorry. That number is 68%. What are these lines things? So this thing right here, let's define a couple things. That is a mu, think like the Pokemon. It's a mu, it's a U with a little line on it. It's not spelled like the Pokemon, it is a Greek letter. It's pronounced mu. You know this one already. It's the average. When we say the class test average was 87%, we're talking about the mu, okay? The other little Greek symbol we're going to use is a sigma. It's a circle with a line over it. Sometimes you'll see the line is a little fancy and curly and all that stuff, but it's really just a circle with a line over it. It's called sigma. There are a couple different versions of sigma as a capital and a lowercase version, but we're going to use the lowercase version. This is for the standard deviation. Standard deviation. Standard deviation is a little trickier because we're used to averages, we're used to seeing them, we add them all up and divide by however many we have, but standard deviation is calculated a little bit differently. These are sigmas right here. Basically it says what's the average that people tend to go away from the average, right? We kind of talked about this in class as well. If I say the class average was 87%, but that doesn't mean anything because a bunch of people got A's and a bunch of people got F's, we would say it has a very large standard deviation. It's kind of all over the place, right? Where if I said, actually, yeah, the average was really close to 87%, a lot of people got that, that would be a very small standard deviation. How to calculate this is going to come up in the chapter, so don't worry so much about that now. I'm going to show you how to use it, how to put it on this graph. But all of these 1, 2, 3, -1, -2, -3 is basically we're adding standard deviations. So back to the empirical rule. Pretty important. In order to be considered normal, 68% of things, of people, of anything that you're measuring has to be in between two standard deviations. So our test example, let's say 87% was the average, but that doesn't mean everybody had to get 87%. Let's say it was a standard deviation of like 5. We would say that it would be normal if 68% of people got between 82 and 92. Okay, so I went 5 up, 5 down. So within 5, right? We usually see like plus or minus 5, right? That's a standard deviation. So as long as 68% of people reach that goal, it's normal. Now we have to be a little more technical, right? It can't just suddenly switch after that. We'd say actually 95% has to be within 2 of them, and then almost everybody, 99.7, has to be within 3 of them. Anybody who's outside of that, we can have like one outlier, one person who's just being really weird and for some reason epically bombed the test, didn't even try, turned in a blank piece of paper, or got over 100, right? And like got the super bonus question, or that was super hard and nobody else got it. You can have one person outside there, but as long as 99.7% is within a certain range, right? And 95 of that is even better, and then 68% is even closer to the average, you've got yourself the normal curve. Okay, so that's the empirical rule. Now, how do we set that? What does that break down to? If you split up that 68%, because 68, right, it's a bell curve. It's got to have 2 sides to 68. You get 34 on each side. And then if you add the difference between the 95 and the 68, you get 13.5 going between these 2 lines. Sorry, these 2 lines here. You get another, we're going to round it off to 2.5. It doesn't equal exactly 100 when we do this, but 2.5%. And then here we get that last 1%, those smarty pantses and those never tries. So this is how a normal curve breaks down. Once you've decided it actually is normal, we would fill in these like boxes with these numbers, and we can actually start making some probability statements about this. So if we know that the stats have told us that 68% of people are between these 2 lines, we can actually make claims about things outside the lines as well. So that's probably the easiest to show you with an example. You would definitely want to put a star by this, because you're going to write it about 100 times in this chapter. So this is the diagram of the normal curve. Okay, so when we say normal curve, fill in the normal curve. This is what we're talking about. Alrighty, let's actually use this in a problem now. So go ahead and jump on over to example number 1. Sorry, my key is easier to read, so I'm going to pull it on up. The height of 1,200 male students at a local high school are normally distributed with a mean of 68 inches and a standard deviation of 3 inches. From this group of students, draw the normal curve for this situation. So, what on earth does that mean? Normally distributed means we don't have to question whether it's normal or not. The empirical rule has already been applied. We know that 68% of people are going to fall in this category. And then they're going to tell us more about the mean and the standard deviation. Notice they just kind of gave both of those to us. We can use that now to create this normal curve. So I'm going to leave a little space on the bottom so we can fill in some numbers. Let's go ahead and draw a curve that looks pretty normal. It's going to have the mean right in the middle. We'll fill that in a minute. Sorry. Heads up, I'm working on my cell phone in case I haven't mentioned it before. I'm using a stylus, so it's going to get a little crazy, but he's all good. All right, we'll fill in some lines. Here was that 34%, 34%. This is the 13.5. This is the 13.5. We have a 2.5, a 2.5, and a 1. And remember, that all comes out of the fact that they told us it's normally distributed. It's already been made for us. The empirical rule has already been applied. So we've got these now. They're always the same. That is a 2.5, not a 12.5. But we need to fill in the bottom as well. They told us the mean was 68, so we'll fill in that. But then they also told us the standard deviation was 3. So where does the 3 go? The 3 actually doesn't go anywhere. It's kind of like with that 87 example. We're going to go up 3 and down 3 in both directions. So up 3 here would be 71. We'd go up 3 again, 74. We'd go up 3 again, 77. So that would be people who are taller, right? You get taller. As you get taller, you get more people who are actually, less people, pardon me, who are actually taller. Same thing going down. We'll go subtract 3, so minus 3. You get 65. Minus 3 again. You get 61. Minus 3 again. You get 59. I'm sorry, not 61. 62. 59. And we've filled in the normal curve. Okay, so now what are we going to do with this? We'll see in B through E. But this is our normal curve. Okay, what is the probability that a male student chosen at random is 5 feet and 5 inches or shorter? How many students are shorter than 5 feet 5 inches tall? Okay, so kind of a two-part question, right? First off, 5 feet 5 inches is not on our normal curve. Everything else was in just inches, so let's convert that. Well, 5 feet is 5 times 12 inches plus the 5 extra, would be 65 inches. Yeah, so we're really looking at the probability of 65 inches or shorter. We can write that in a kind of a technical way. What is the probability that a student, we'll call him X, is less than 65? You can say less than or equal to. That's fine too. Or equal to kind of gets roped in a normal curve either way, so it's not, you probably won't see a lot of equal to, but it's not super technical either way, to be honest with you. Okay, so how do we do this? Well, let's go over here. Let's go back to our normal curve. The reason we drew this whole thing is it's going to tell us those probabilities. These numbers here are the probabilities. The 34 is the 13.5s. So here, right here, we see 65. Anyone less than that would be in the 65, 62, 59 zone. So we're going to just add up those probabilities. We're going to add the 13.5 from the 62 to 65 plus the 2.5 from 62 to 59 and the 1% of anybody who's below that. And we get an astounding 17%. So there's a 17% probability that we get less than 65 inches. Cool beans. Now, what does that mean for how many actual students? Well, that's a different question, right? We don't say 17% of the students. We know that there are 1,200 male students, and so 17% of 1,200 means 1,200 times, well, I don't want to write it in a percent. That's kind of hard to plug in a calculator, so let's do it as a decimal. 0.17. Remember, to convert to a decimal, we just need to take that point and move it over 2 places. Right? Percent means per 100, so we're dividing by 100, moving that decimal place over. We get 0.17. Times that by 1,200, since the decimal, that means that number is going to go down. We get 204 students. So according to this, 204 of those students, that 17%, were less than 65 inches. And we've answered both questions. All right. If you have a question, you can call the sub over, but I'm going to keep going. The video is going to get pretty long, so just call the sub over, but keep writing. All questions should probably be answered at the end. What is the probability that a male student chosen is at least 5 feet 5 inches tall? How many students are at least 5 feet 5 inches? Almost the same question, but now it's not or shorter, it's or above. So what is the probability? We already converted 5 feet 5 inches into just inches, so 65, greater than or equal to 65. The other half. Now there's 2 ways we could do this. We could go back to our line, our curve, find that 65 again and add all the things up on the other side. But since this should equal 100, or pretty dang close to, why don't we just do everybody else? The 100% of everyone minus the 17% of everybody else. Everybody who's not over 65 feet. And so we get, 65 inches. 65 feet would be crazy. 65 inches. In other words, 83%. You would have found around the same number if you added up the other side. You would have found 83%. Alrighty. But we also have how many students, so same routine there, the 1,200 in total times the 0.83. We could also just subtract 1,200 minus 204. Either way, we're going to get 996 students. And so we can see this helps us, this curve is helping us answer questions for both above and below a certain standard deviation line. Alrighty. What is the probability that a male student chosen at random is between 5 feet 5 inches and 5 feet 11 inches? So now we've got a between situation, both of them not quite in inches, so let's convert this one. We already know that one, that's 65, but 5 feet 11 inches is going to be 60 plus 11, or 72 inches, right? The 60 inches and then 11 more. So we want the probability, how do we write between? Well, we're going to have an x. It's got to be greater than the 65, that person does, and he has to be less than 72. So we get this kind of combined 65 is less than x is less than 72, so someone in between. We get a combined inequality. So same routine though, we'll go back to our normal curve now. Where is 65? Let me grab a different color. I know we're on a different problem. Here's that 65 again. Let's see, 72. Did I do my table wrong? I'm sorry. Sorry. That's 72. 71. Let's try that again. I can add. 71. Not 72. Okay, so 71 is right here. 72, we'd kind of be at a loss, right? We wouldn't be able to find a line that actually fits because we don't know anything about 72. But we've got 71 anyway. So here we see, oh, it's between those two marks. Oh, that empirical rule. They're both one standard deviation. Cool. Add up 34, 34. We get 68%. 68% is between 65 and 71. All right. How many students are shorter than 6 feet 2 inches tall? 6 feet would be 5 times, no, not 5. Pardon me. Here's where I was thinking of 72. That's what it was. 6 times 12 inches is 72, plus the 2 inches more, 74 inches. So really, we're asking how many people are less than 74 inches. I can't really find that until I know the probability that someone is less than 74, pardon me. So let's find the probability that somebody is less than 74. I'm going to go ahead and say it's probably a lot. When you look at our graph, 74 is chilling over here. That's a lot of stuff below it, right? So one of two ways to do this problem. We could kind of do it the way we did B, where we add them all up. Or we could do the way we did C, where we could take actually the other side, since that's going to be the other people who are not. You know, maybe we can add up that side, because it might be faster, and then subtract it from 100. I think I'm going to go that route. So the knots, we take 100 of everybody away from the, I don't know, I think it's 2.5 plus 1. We get 100. Oh, take away the 3% who's not, it looks like 97%. 97% of people, okay, I won't round it that way. Just kidding. We'll do it right. Minus 2.5, 3.5? Yeah, minus 3.5 would be 96.5%. Because really that 0.5% counts, right? All right. Super cool, but wasn't really the question. They want to know how many, so let's go ahead and times the 1,200 by the 0.965. Still only goes over 2 decimal places, but now I have that 0.5 to deal with. And we get 1,158 students. All right, cool. So that's all the things you can kind of see out of a normal curve. Let's go ahead and jump over to a different situation now. On a recent math test, the average score was 79 with a mean of 7. That's totally a typo. The average was 79. The standard deviation was 7. Sorry about that. Assuming a normal distribution, what is the probability that a test taker chosen at random scored higher than 86? First, draw the normal curve. Okay, so what is the probability? We need to draw the normal curve. Let's do it over here so we have some room. Remember, we want to leave kind of a space on the bottom so we can fill in that mean and the standard deviations. Let's go ahead and draw the normal curve. Okay, mean, 79, goes right in the middle. The stuff inside the normal curve is always going to be the same. You can choose whether you want to do that now or later. I think I'm going to do it now. 34, 34, 13.5, 13.5, 2.5, 2.5, 1, and 1. On the bottom, it's going to change with the mean and the standard deviation. So the mean, 79, goes right in the middle. I'm going to add 7 going up, 86. Add 7 going up, 93. Yeah. Add 7 going up, 100. Now on the other side, I'm going to take away those 7s, 72, 65, 58. All right, and we've drawn the normal curve of the scenario. Okay, so now what is the probability that a test taker chosen at random will score higher than an 86? Well, here's an 86. Higher than that, probability, x is greater than 86, would be the 13.5 between 86 and 93, plus the 2.5, plus the 1. Oh, again, we see 17%. Cool. Alrighty, what about scoring lower than a 65? Probability x is less than 65. Same routine, same routine. Here's that 65. Looks like 2.5 plus 1. Or 3.5%. Oops. My point got all weird, but that's just a point. All right, now what about between 68 and 86? So 65, x is between 86. So what is the probability of that? And yes, you do actually have to write the probability statement, okay? You can't just write 17% on the page. You may see in some of the homeworks I did, please write the probability statement. All right, we add all that up. Let's see. Here's that same 65, that 86. Two ways to do this. We could take away everything that is not in those, since we already know those, or we could add up the stuff that's in between. Either way, we're going to get 86.5%. Hold on. This doesn't sound right. Yeah, that's not right at all. Just kidding. 100 minus 17 minus 3.5 would definitely be 79.5%. Alrighty, and we are done with the problem. Moving right along. The survey shows that prices paid for 2-year-old Ford Mustangs are normally distributed with a mean of $28,500 and a standard deviation of 700. Consider a sample of 10,000 people who bought 2-year-old Ford Mustang vehicles. How many paid less than $27,100? So, got to build that normal curve, right? It doesn't tell us to, but we can't really figure it out until we know that probability, right? So let's go ahead and build that normal curve. Here we go. There's our mean line. Okay, we have the 34, 13.5, 2.51, 13.5, 2.51. All right, and then right in the middle we have that really long number. I think I'm going to use K for 1,000, so 28.5K. If we go 700 down from that, we get 27.8K. Keep going, we get 27.1K. We go one more down from that, we get 26.4K. You did not have to use the point system. You can write $26,400, but I just think it's, obviously with my stylus, a little hard to fit that in. Going up, we see 29.2K, we see 29.9K, and 30.6K. Okay, we have the normal curve. So now we see that 27,100,000 is right about here. And so people who paid less than that, well, the probability of less than that would be, whoops, would be equal to about 3.5 when we add all that up. But then we have to times that by the 10,000 people who actually did this, who actually, took this survey. Well, 10,000 times not 0.35, because that's 35%, but 0.35 would be 350 people. Okay. All right, how many paid more than 27,800? Well, I can use that same chart, luckily, because it took a long time to make. 27,800 is right here. The probability of that would be, so greater than 27.8K, is 13.5 plus 34 plus 34 plus 13.5 plus 2.5 plus 1 would be, oops, should not have put a 13.5 in there, right? Because it starts at 34. So it's this half of the graph, because there's that 27.8, sorry, minus 13.5. 85%. 85%. And then that times the 10,000 would give us 800. I think it's 8,000.85. So 0.85 times the 10,000 people. Yeah, it's going to be 8,500 people. Which makes sense, because it's got the average in there, right? And we can see how much a curve that is compared to the 350 people who got a really good deal. All right, how many paid between 26,400 and 29,900? So let's take a look at that. What's the probability of that? 26.4K to 29.9K. And we get, let's see, the probability of that. Let's see, we got 26 is chilling over here. I'm going to use different colors so I can see what I'm doing. Green. Here's 26.4 all the way up to 29.9. So 2.5 plus the 13.5 plus the 34 plus the 34 plus the 13.5. 97.5. 97.5%. But that's not really the question, right? We don't know how many paid, so times that, times that in decimal form, times 10,000, 0.975 times 10,000, we get 9,750 people. Try not to forget your units. Alrighty, cool. One more down. Before we hit the last one, kind of try it on your own. Pause the video if you can. Don't pause too long because we don't want to take too much of class, right? But, pause for a minute, see if you can get it before I do it for you. I'm just going to stop talking for about 10 seconds, give you guys time to pause that, and then pick it back up when you need to. Okay, so hopefully you had a chance to try this one on your own. A gas can't talk today. Miles per gallon of cars driven by high school students is normally distributed, so that's good, with a mean mu of 22 and a standard deviation sigma of 4. Find the probability that a student vehicle chosen at random has an MPG greater than 26, less than 14, between 18 and 30, and less than 26. So, kind of the same thing we've been doing, just probabilities this time. Let's go ahead and draw that normal curve. We got 22 as that mean. 26, going up, 30, 34, up by 4 each time. Now down by 4 each time, we get 18, 14, and 10. Then we'd want to fill in 1, 2, 13.5, 34, 34, 13.5, 2.5, and 1. Right, same as always, that didn't change. Okay, greater than 26. There's 26 here. Whoops. So 13.5 plus 2.5 plus 1, 17%. The probability that x is greater than 26. The probability that x is less than 14 would be 2.5 plus 1, or a whopping 3.5. That's good. We don't want people failing. Or we don't want cars. Actually, no, that wouldn't be good. Just kidding. It's not a quiz. We would love it if more people had below that, right? Because less emissions, less gas, blah, blah, blah. Oh, no. I read that backwards. Sorry, this isn't miles per hour. This is miles per gallon. We don't want that. We want more people having more efficient cars, right? Anyway, so then between 18 and 30, that would be right here to there. That'd be that 68% from the empirical rule plus the 13.5. We see 81.5. And then less than 26. Let's see, 26 is right here. That's a lot to add up, so you could go either way. It's kind of almost 50-50, but you could do the 34, 34, 13.5, 2.5, and 1, or you could add the other side, which was, we already have 17%. If you add the 34 plus 13.5 plus 2.5 plus 1, you get 85%. And if you go the other way, you would get 83%. On a multiple choice test, you'd probably see well, actually, it's kind of a 50-50 shot about which one you'd see, which is annoying. But that's kind of a thing about stats, is that stats is not the cold, isolated calculusness of math as much as you'd think it would be. It is very fluid. This chart's not perfect. There's going to be people outside of these ranges, right? We already changed 2.35 down to 2.5, and even before that, it's really actually not even 2.35. So you're going to get a little discrepancy. It's going to happen depending on how you do it, and that's okay. Just go with the one that is the closest, okay? And if you're worried about it, then you can come, you can email me, I can explain what to do, or you can talk to the sub, okay? Either way is fine. I'm still grading your test, by the way, so it's still me. When I did it the first time, I went the 83, because I'm lazy, right? So if you wanted to do 83, it's fine, but 85 is also acceptable. All right, that is basically the normal curve. You now have plenty of homework time. You can get some homework done out of the way, and then the day is yours. I'll see you in 7.2.